There are some rules in life. There's the 5-second rule, where if you drop something, it's still clean as long as you pick it up before 5 seconds. For the record, I've never believed this rule. Chemistry has several rules of its own. The octet rule in the main group, Markovnikov's rule in organic chemistry, Hund's rule in electronic structure, and Lipinski's rule in medicinal chemistry, to name a few. The most important rule of chemistry is, of course, never lick the spoon. A simple guideline or rule can save a lot of time when you're trying to understand molecular systems. In this video, I'll talk about Bent's rule, which is a simple way of understanding electronic structure preferences for an atom and a molecule. In this case, it is helpful mostly in the context of hybridization theory, and we have a growing video series on hybridization theory. Bent's rule, named after Henry Bent, a former professor and physical chemist interested in MO theory, hybridization theory, and thermodynamics, his formulation of the rule is atomic S-character concentrates in orbitals directed towards electropositive substituents. Let's look at what this means and why it's helpful. The simplest type of system to look at for this is anything with a lone pair and a bond on the same atom, so something that happens all the time in compounds as common as water and ammonia. Let's use something more exotic, phosphine or pH3 with one lone pair. In the lone pair and in the phosphorus-hydrogen bond, there are 2 electrons. In order to best stabilize those electrons, phosphorus will adjust the amount of S-character and P-character in the bonds. Since the S-character is lower in energy, it can best support electron density on its own. For the electrons in the pH bond, the hydrogen nucleus will help the phosphorus stabilize the pair of electrons in the bond. As a result, phosphorus will use more of its higher energy p orbitals here since it has help supporting the electron pair. For the lone pair, however, phosphorus needs to support the electron density on its own, so it will use more of its most stable valence orbital, the s orbital. We can think of the electrons in the lone pair as being involved in a bond to a group with an electronegativity of 0. The phosphorus gets no help at all in stabilizing the electrons. The higher electronegativity hydrogen helps stabilize the electrons significantly, and as a result, the phosphorus uses its higher energy orbitals here. We can quickly use hybridization theory to analyze pH3, which has an HPH angle of about 93 degrees. Again, this type of analysis is discussed in earlier videos, so if you're interested in learning more about how to do this, please check those out. We have equivalent bonds in pH3, so we can use the simplified form of the Coulson directionality theorem, which is this. We insert the 93-degree angle and get that the hybrids on phosphorus used to make the pH bonds are a very large sp19. So the pH bonds are being formed with nearly pure phosphorus p orbitals. We can use the sum rule to get the nature of the lone pair. All the sum rule says is that there are 3 equivalent pH bonds in one lone pair, and if you add up the amount of s-character in those hybrids, it must be equal to 1 s orbital that you started with. The pH bonds are largely p-character, using up much of the p orbital character available, so one would assume that the lone pair is almost entirely s-character. The sum rule confirms this, giving the hybrid that is used to hold the lone pair as a very S-rich sp 0.18. This is very much in line with what we expect from Bent's rule. More generally, Bent's rule suggests that if you have 2 different groups on a main group element, the more electronegative group on the central atom will better support the electron density in the bond, allowing the central atom to use more p-character. Let's look at a different example where we have no lone pairs but different bond types. For fluoromethane, we get a geometry that has 3 equivalent CH bonds with angles of 110.3 degrees between them. We can analyze the electronic structure here to see how the structural perturbation has affected the electronics. We have equivalent HCH bonds, so we can start again with a simplified Coulson directionality theorem for equivalent bonds. We get that the hybrids are slightly more S-rich than in methane at lambda CH equals 2.9. We can check the values like this using natural bond orbital theory. NBO and valence bond theory are related in that they both use orbital hybridization. However, the details of the calculations are quite different. For here, all you need to know is that the software that uses NBO, here we're using NBO 7, can be used to get these hybridization parameters from calculated electron densities. NBO gives essentially the same value we calculated using the Coulson directionality theorem at 2.7. Analysis of the CF bond can be done using the full Coulson directionality theorem with the now known CH bond hybridization. The full expression for inequivalent hybrids I and J is this. The HCF angle is 108.6 degrees. We also add the now known hybridization for the CH bond. We can take the reciprocal of both sides and square. This gives approximately this, which provides the hybridization parameter for the CF bond is 3.4. MBO gives a slightly higher value at 3.9. Note that the higher hybridization parameter in the CF bond relative to the CH bond is consistent with Benserol. More atomic S character is being used in the bond to the less electronegative hydrogens. Here are a few more complex examples of using the Coulson directionality theorem to find hybridization parameters and illustrate Benserol. What if we have a trigonal compound with 3 different groups? We end up with a system of equations. Let's take a look at a system like indium fluoride chloride hydride as our example. There are several ways to solve this, and I'll solve for a general case below, so we can apply it to anything, then show how it can be applied to this specific problem. For any main group system with 3 different groups, x1 to x3, with unknown angles θ1 to θ3 between them, we can define the system like this. The X groups can be attached to any normal or hypovalent main group system. In other words, it doesn't necessarily matter if X has a lone pair or another group. As long as there are only 2 center 2 electron bonds in the system, you can use the solution we'll derive. We want to solve for lambda x1, lambda x2, and lambda x3 in the system of equations below. To simplify things a bit, let's make the replacement alpha ij equals negative cosine ij. Square each equation and rearrange. To solve for lambda x1, we can multiply the first and third equation and divide by the second. We then simplify the left side to get this. Taking the square root of both sides gives the simple equation after taking the positive root because hybridization parameters are always positive. Then we replace the alpha ij terms to get the final equation. In other words, the hybridization parameter is equal to the negative cosine of the angle opposite of the group of interest over a function related to the adjacent angles. For indium fluoride chloride hydride, we can find the geometry from experiment or calculation. In this case, I used DFT to find it, and it is shown below with the angles. We want to solve for lambda h, lambda f, and lambda cl. We can use the Coulson directionality theorem as a system of equations. Here is our general equation again. So we can find the hybridization parameter the indium uses to bond with hydrogen by simply using this equation. And we find that lambda h equals 1.31. Applying the same formula to the other 2 groups gives lambda f equals 2.70 and lambda chloride equals 2.37. Benserol predicts that the S character, as shown by the low hybridization parameter, will concentrate in bonds to low electronegativity groups. The MBO values are only slightly different than our by-hand calculations and also are very much in line with Benserol. Finally, let's find the hybridization parameters to all of the groups in a tetrahedral system where the tetrahedron has 4 different groups. Again, we can get a system of equations, and all we need to know is the geometry, which is the input for any kind of electronic structure analysis. For a tetrahedral or pseudotetrahedral system, there are 6 angles and 4 vertices. As a result, the hybridization parameters are overdetermined by the angles. Ideally, we would be able to use all the data to determine the lambda values. Here is a general solution for a tetrahedral system that does this, and then I'll provide a derivation, which will build on the derivation of the trigonal system above. In this scheme, each ligand is labeled x1 through x4, and the angles between, say, x1 and x2 are given as omega ij. It is then simplifying to use alpha ij equals negative cosine omega ij. The lambda ij values are then given by this, with the example being for ligand x1. To get this equation, consider that for the Coulson directionality theorem, cosine omega ij equals negative 1 over the square root of lambda I times lambda j. Substituting with alpha ij equals negative cosine omega ij gives this. Rearranging and squaring gives this. Previously, we derived the equation for a trigonal system with x1, x2, and x3 and 3 angles. The hybridization parameter is based on the 3 angles in the system. In a tetrahedral system, there are 3 trigonal faces around x1. They're x1, x2, x3, x1, x2, x4, and x1, x3, x4. We can create 3 different estimates for x1 using the 3 faces. Then take the geometric mean of all 3 estimates. The 3 estimates are then this. Multiplying all 3 gives, and taking the cube root to get the mean gives the equation for the hybridization term related to the substituent x1. Let's apply this to a simple tetrahedral system with 4 different groups. Silicon with a methyl, bromide, fluoride, and chloride. The angles for the system from a DFT calculation are tabulated here. We can use the equation above with the 4 groups and these angles to get lambda values. I'll spare you the actual calculations, but here are the results. Again, we can compare with the values from MBO. The by hand values and MBO values are in pretty good agreement, but both sets of numbers are again consistent with bench roll all the way across, with the hybridization parameter and electronegativity of the group going as methyl less than bromine, less than chlorine, less than fluorine. We're over-parameterized, so if we back calculate the angles from the hybridization parameters to see how close we are to the original angles, we find that our values are pretty close, with the largest deviation being 0.4 degrees. The fact that hybridization of the orbital used to interact with the group and the nature of the group are interrelated means that we can adjust the geometry of a molecule just based on the groups. As an example, you know simply by looking that the FCF angles in trifluorotoluene, where carbon will use more p character, are smaller than the HCH angles in toluene. It can be used to quickly refine structures that Vesper will tell you are the same. Further, it tells you why the structures are different. One quick note about our by hand versus MBO calculated values, in case you're wondering why they aren't exactly the same. The answer is that we've been making an assumption in our by hand calculations, and it's a pretty good one. We've been assuming that the hybrid orbital you're generating is pointed directly at the atom. You'd expect this to be the case, since this would maximize overlap with the bonded group, and it usually is. However, there can be deviations from this for a few reasons, which is called bond bending. So the slightly different MBO values are typically due to hybrids that don't quite point at the group for some reason. We should probably make a video talking about some of those reasons sometime, and that'll probably happen pretty soon. So there's a quick overview of bench roll and how it happens to apply to main group and SP hybrids. It can help you quickly understand why a structure is changing and how it will be changed with different substituents. There are compounds that are not compliant with bench roll, which can happen due to bond bending. But for the most part, compounds obey this simple rule. Thanks for watching. We make these videos for fun and to give back to the community. Please subscribe, give us a thumbs up, and take a look at the rest of our playlist, which has videos at a variety of levels. Hit notifications so you don't miss anything because we drop vids only occasionally. Thanks.